Sorry for being a bit late. I was checking the back of the dunny just to make sure it was at an appropriate water level. American toilets are a bit too high, but we're not talking about that today. We're going to be talking about learning Rosetta 2, the translation layer at macOS for previous Intel Macs. We're going to learn it with game hacks, so let's get into it. So, a little bit about me. I'm a mature age undergrad student, currently at RMIT, which is in Melbourne, Australia, so a bit far away. I previously was in the cloud migrations team at Atlassian, and now I have an interest in reverse engineering and firmware, and I especially like breaking my MacBook. So we'll get into, I guess, the broad overview of the talk. I want to show you how to make a really basic God mode cheat in a video game. But what the hell is gaming on macOS? Look, it doesn't exist, right? But we'll try our hardest. It's usually via Rosetta 2 if it's an Intel Mac binary, which is most often what it is on a game. And then we'll get into how that works, how that influences how our cheat is going to run, and then we'll show some other evil things. But look, the real secret objective is how to get banned off GitHub. So yeah, if I share, I'll share this on my blog after this talk, but yeah, if you too want to get banned off GitHub, you can do it in 3 easy steps. I'll also preface why I love using the MacBook. So I'm gay and I love garbage. People often say, if you're garbage at computers, you're on macOS. And sweetie, that's a little something we call a hypothetical syllogism. You know, A if B, such and such. So I'm using a MacBook. We'll get into the game that we'll be playing around with today. Assault Cube. It's an open source version of Counter-Strike, essentially. It's actually a really common cheat developers, you wish, cheat developers use to learn how to make a cheat for a video game. There are other examples like old SimCity editions and Counter-Strike 1.6, but the reason why this is really fun to use is because the anti-cheat is enforced on the netcode level. So as long as you're doing like local play, you can pretty much do whatever you want. I was inspired because Jai Verma, B-Sides Mumbai 2018, initially did this for Intel Mac. So obviously a lot of game cheat developers are going to be doing it for Windows. And he did a really good talk on doing it for Intel Mac. But I'm on my trendy Apple Silicon MacBook. So how the hell am I playing this? That goes into our other topic, right? It's going to be Rosetta 2. So Rosetta 2 is what Apple used to essentially make the transition to Apple Silicon, which is ARM, a bit easier. I would say if you were wanted to describe it in a sentence, it would be easy to say, oh, it's an emulator, but it's not exactly an emulator in that it keeps the machine above. It's just a transpiler. It's translating all those 86 instructions in an original Mac binary that's made for Intel, and then just on the fly or ahead of time, doing some translation of that into native ARM instructions. So it's still on everyone's MacBook now if you choose to install it. After the next major release, it's technically going to be end of life. I don't know if that means it's going to get removed or there's no more support, but they're essentially trying to bifurcate into 2 things, which is the virtualization I think they put out in the last WWDC, and then so that's going to be mostly Linux VMs. And then there's going to be the game porting toolkit Windows evaluation environment, which that is such a mouthful. But the long and short of it is it's for people who want to port their stuff to Mac and they're game developers. But honestly, let's be real, that's just our new Proton. So we'll see if anything from Rosetta goes into either of those 2. Some of the concepts I'll go through today. I want to get into how it does some of the Rosetta stuff so we get a grounding of how this all works. There's two general steps, really broadly. So there's the ahead of time translations. So when you first run a Intel Mac executable, that syscall, if it knows that it's an 86-64 binary, a daemon, which is OAHD, is going to check it and say hey, I'm going to calculate a really quick hash based on a few parameters of a file, and I'm going to see if that's in our ahead of time cache. And that essentially means, have we got some ahead of time translation already, or do we need to do it? And if it doesn't find it, we're going to just essentially shred your CPU, and that battery life statement that we make about our huge battery life is not going to really last, but it'll be once, and it will do as many one-to-one translations from 86 to ARM. And it's usually pretty verbose because we can't use all of the cool stuff that ARM has for like aliases, like, you know, if you use addS and you want to add flags after it. So it's pretty big. But when this is done, we just save that file in the var-db OAH directory, and then we don't have to do it again. And that's kind of, so if you either get it or you don't have it, no. We essentially just have that section for the ahead of time translation. And then we have the just-in-time translations. So I think the easiest one to think of this is like external like functions you might be pulling in from a library. That will be stubbed in the ahead of time translation. So a really simple one is like puts. That's just going to be stubbed into the AOT. And then when it gets resolved by Rosetta, the just-in-time translation is going to say, like, hey, I need to look up that, I need to find it, and then I just need to pass the function pointer to it, and it's going to be a jump to that specific function. So that's essentially what the just-in-time does. It's for a lot of other things that are not deterministic, but that's the main idea. The really crucial thing about just-in-time translation is that it needs to look at the original 86 code, right? So we need to keep state of all those ARM instructions, and then make sure we can look at the original instructions that were on that 86, 64 binaries. So it's really important that runtime knows what instruction is at 86, so it can then go through like a red-black tree to see what's going to be the most useful translation. So that, I mean, implicitly that means it's all getting mapped when you run a Rosetta process under Rosetta. And that's that bit. So look, this is like a lot, right? This is like a bit much. You could just like not do that, like, I don't know, every other Apple thing. But look, the idea was that they wanted to smooth out the transition because they knew moving to ARM, like, especially earlier on, was going to be pretty hard. And the reason why it's really verbose is they want it to be, one, really fast to do that initial translation for like the bulk of like quite repetitive code. And two, they wanted to make it pretty easy for like a developer to move to Apple Silicon. So if we're keeping state of essentially where the PC is, the counter, so which instruction is being run, we can also give that to a developer. So when you do LLDB on a process running under Rosetta, you essentially get all the registers you're used to on 86, you get all the instructions from the original 86, and you're kind of like just not being shown any of that ARM, whether it's interpreted or ahead of time. So that actually makes it pretty easy to be like, oh, suddenly, I don't know, floating points broke or something, but you can see the actual instruction on 86. So that's pretty cool. And the reason why that ARM is pretty verbose is because it wants to mimic everything about 86, right? So there's going to be like 3 implicit instructions for a push in ARM, whereas that's just like one thing in 86. So that sucks, but we can work around that really. Like we can make a specific Rosetta return stack where we can put all those addresses in a special place so we can mimic return address prediction, which is in 86. So don't even worry about it, babe. This goes over like the Rosetta stuff. Whoops, I didn't go on that slide. But another thing is also that the AOT translation is fast because it's really verbose. It's not doing any cool optimizing. But I was thinking about it like last minute, and I was like, why do we need to optimize something that's probably already been compiled with like the craziest flags I would not know in Clang? So it's probably pretty good anyway. We'd be squeezing like blood out of a stone at that point. And we want to use that ahead of time translation because we can leverage all the implicit stuff I don't know about, like what the sand block does on my machine, to speed up execution anyway, because we're not using as much just-in-time translation, and we're leveraging the fact that it can read all those instructions that are quite repetitive. And yeah, I'm showing it again just to make sure everyone's across it, and I've realized I've kept the little box there as well, so whoops. And this is kind of like how it looks in a process. So you can see that we just get mapped the runtime, and we get some other things for the library. Don't look at the evil stuff, that's for later. But I kept that because you can see actually the OAH. So you can see that evil dilib AOT. That's essentially what is running. But obviously it's not all the code because it might be stubbed with other functions that are outside of evil dilib. So the runtime will look at it and then say like, oh, I need to add some extra stuff, whoops, sorry, and then send it back up. Okay, we've talked too much about like all this crap. We've got to get into like a game hack. So really simple, like almost like hello world of making a game hack is usually going to be health. If you ever look at like a bunch of like forms for it. And I used to be like, well, that's not fun. I want to like pretend to be good at a video game instead of like being bad at it, but they can't kill me. But it's actually a really good idea if you're like writing a game sheet, because we want to find memory that is easy to edit, and health is usually going to be like an integer of some sort. And we want to manipulate it, obviously, because we want to make it a God mode cheat. Reverse the value, so we want to see like initial declarations, and that kind of walking through like dereferences and pointers to what that final value is. We're actually probably going to be co-located to a lot of other important stuff to a player, because why would they like, I don't know, malloc like, I don't know, integer health, and then like 100 other lines down they'll be like, oh yeah, and also give this guy a gun. They want to do that all at once. So it's usually co-located probably in a struct where there's all these other types for a respective player. So now we just kind of have to go looking for it. We could use LLDB, but I really like using BitSlicer. BitSlicer is a tool on macOS which is almost similar to like Cheat Engine. I would say it's a bit more, it's less verbose in its scripting, but it's really useful outside of video games because it gives you like really powerful ways to look up the malloc region. So I really like using it. Also, it's like, I said it like last night, but it's like Photoshop. I don't have to look through the terminal. That's different and cool, but look, I'm used to it at this point. So we just want to change the value a few times, and then we can see what is happening in memory. So we can search, like, say, like 100, take some damage, change it to a different value, and then just roll through a bunch of different things in that region. And then we can finally get like only like 1 or 2 candidates, where one might be a dereference that goes into the UI, and one might be the actual value. And that's pretty much it, right? Now we have like this value, and we can just, you know, edit 99999 like I do in Cheat Engine in SimCity, and I want $1 million. But that gives us an idea of like how we can see if this is like a dereference, and walk through where this initially gets made, where the sausage gets made for a player. And that's what you want to do, really. So after you've found that value, I like to set a watch point. So it's essentially just a breakpoint, but you just want to see memory access. And I can see, oh, this is the other thing I didn't mention about BitSlicer. I can just see like the arm. And like LLDB will like shim all the 86. And like, honestly, I'm really bad at reading 86 at this point. So I'm like, yay. So you can look through here and you can see, look, it's storing health into x15 plus 418. So you can go, okay, I have 2 things I can look for. I can either look for any pointers that contain x15 plus 418, or I can just look at that value at x15 and see if there's anything that contains that as a pointer. And usually the go is to check the thing without the indirect addition. So I just went through x15, and I looked through a bunch of different pointers that contained it, see if there was a pointer that contained that pointer, and so on. And then we're there. So we get the initial value for health. This is a little bit interesting in Rosetta because I'll give an example, not for like an integer, but say you have a string and you've just hard-coded that string and it gets compiled and now it's just there. Rosetta's not going to translate that because that's not an instruction, that's just a label to like a string. So it will just then stub and say like, hey, just go back to the 86 and look at that. So sometimes you'll get like pointers to pointers to pointers to pointers to pointers to pointers, blah, 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 blah. And that's, look, I'm so glad that's an integer. I mean, imagine if your health was like a name. Good, bad, average. So that's awesome. We've got the value. We can do like some napkin math, or we can look at VM math to do that. But I wanted to walk through people a bit around the hell that is the mark library, because it's barely documented, or it's documented really poorly unless you like have an Anna's library copy of macOS internals, or you get a valid copy. But essentially, we just want to look up one specific thing there, VM region basic info. I've got rid of a bunch of it, but it's just declaring all these different things within the VM region. And essentially, we just want to query that to say if there's read and execute enabled. And that's essentially what's going to be like executable instructions more often than not. So that's how I would go for it if you wanted to practice, maybe just writing little scripts and seeing if you can find like, executable and readable regions in memory. The Rust library for it is pretty good because they detail everything it does, even if you're not writing Rust. So the muck cargo crate for it is really good. All right, so we know a bunch of stuff about where the health value is, but how do we do it? Well, we know that instructions are being stubbed in, and then the just-in-time that Rosetta has resolves it. We know that the dynamic linker kind of works like that as well, where we essentially have like pointers that are garbage values, and then the dynamic linker is going to say like, hey, you have this library in this process, let me give you the function pointer for it. So that's cool. But the thing is, code signing is like a thing, and like that sucks. So that's a real pain because there's like a header region in a lot of, in muck executables or muck files where it's going to check a code signature and then not the dynamic linker, but something else will check it and say, oh, I don't think this matches, so I'm going to spit the dummy and give it up. But I don't know. Damn, that's hard. I don't know what to do with this. No, it's fine. Yeah, you don't have to worry about that. So it does read it. And actually, if we looked back to this, it's still, like, we're obviously keeping the original 86 instructions, like that hello out, that's fine. But we're also looking at for like headers and code signatures and stuff. So I don't know, it doesn't matter, but it gets read. So cool, that's awesome. So if you've ever used like LD preload, if you have a game that like barely works on Linux, you can do a very similar thing with this in mind, which is the DYLD insert libraries, which essentially just say, hey, load this thing first, please. Or like when you start going through it, just load this. And we can just do that. So I'll go through like a bit of pseudocode to actually get this going. So we just want to get that base address because we know it's like base address plus an offset. So we can see that we're just saying, get me the first image header, and that's going to be obviously base address. And then we can just essentially store the offsets we found. So I went through it a bit quick, but there's going to be like base plus 1D90F0. Then it goes to our little pointer that gets plus 418 for that store into the health. So we can just walk that. So we then just walk it, and if we get 0, I don't know, we print whoops. And then once we've got it the final thing where value gets changed, we can just change it to 999. And that's pretty much how to make like a really simple first game sheet, really. You can make an internal one, like I've described, or you could use an external one where you can use like inter-process communication to essentially tell the process, hey, do this for me, please. A lot of this is considering like how anti-cheat works. So you're editing values, but like who's watching, where can it watch from, et cetera, et cetera. So internal is going to usually be like the easiest, but a lot of anti-cheat can grab that. So a lot of people like do external stuff or like hardware now at this point. So, and yeah, that's pretty much it. I've like pulled this all out so you can see like the little value get changed in like the bottom left, and you can just get a really simple cheat going. So I can continue being bad. If we wanted to make an aimbot, this is like essentially like where you can start because health is going to be co-located to a lot of other player values. So you can see that there's a few floats just at the top of bit slicer there where we're moving around. So we can get XYZ. And then all we would have to do is like maybe look for like that player struct and see if it's being referenced anywhere else, and we could potentially get a list of pointers to other players, and then we can yada, 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 and then go through all that. Oh, this isn't finished. Yeah, what if I like wanted to make a game because it doesn't run unsigned code that like fucked you up? And not like a hack, like I wanted to fuck you up. So like we know we can run unsigned code in Rosetta, right? That's actually not as common anymore. So like iOS, as far as I understand, requires it. We know that DYLD and like a kernel tool will check that code sign and like spit the dummy unless it has like an entitlement in a plist, which is like essentially just saying like, don't worry. But because we know it's like okay in Rosetta, there are a lot of examples of like people leveraging the fact that you can just run almost whatever. So I think the most reported on one is PullRat. It's like the most LinkedIn blog post, like North Korean malware. But it's like a patched open source cryptocurrency, yada, yada, yada thing. But the long and short of it is that they either compiled it for like Intel Mac, or they made a universal fat binary, which means it has both architectures, which is like a bunch of apps that Apple lets you make, and they want you to make it like that. But they explicitly want it to run in the 86 mode, which then goes under Rosetta. And that essentially means like they can start at least with the idea that, yeah, it'll be running under 86, and there's some other things we have to consider with it being under Rosetta 2, but we know that we don't have to do code signing. So there's I think the latest one was the Mandiant report. I'm saying that's so Australian, Mandiant. But without going into like the full guts of a sample, essentially it was a Python 2 script that pulled down like an Intel Mac executable, then Rosetta ran it, and it did as much for one-to-one translation that ahead of time, and then it would just stub a function, and then that function was a library that was just like, I'm going to call out to C2 and be like, hello. And that's essentially how a lot of these crypto scams got fulfilled with PullRat. So there was like at the end of the report saying like what you can do against it. And since we're saving like a lot of the instructions with the AOT, you could technically do a bunch of forensics, but it's in a directory where you can't access it unless you've disabled the system integrity protection, which is not good. It does get tracked by unified logs and FS events by default, which is just like the logging. But in terms of like being specific about like what Rosetta, the runtime is doing, or like what file is being pulled from the OAH AOT cache of all these translated files, it just says private by default. So it's pretty hard to do like a bunch of forensics against it. And there are some other quirks around like how the hashes get calculated for that initial like I'm going to chuck in so-and-so directory. So if you know how that hash is calculated, you can essentially chuck almost whatever in there. So it is actually really helpful and honestly kind of easy if you have like that AOT file and if you had like an idea of like adding a custom profile after the fact. So this is not good, babe. This is like really bad. It is like intentional. I don't even want to say like a CVE because it's like intentional, right? It's designed to be this way. It's designed to be friendly. There are a lot of reasons why they're retiring it, probably because it's really hard to maintain as well. Like you'd have to think that they're shipping like all the system dynamic libraries in this Intel format alongside, or they're translating it. There's so much that probably goes into it that this is probably the least of their concerns, that someone's running like the dodgiest application alive. So these are like ideas I had for like what you could do with Rosetta 2 in a video game. But it would just be injecting code via a library, so it's doing an external function, and then the Rosetta JIT and the dynamic linker are like tag teaming. So they're doing lazy binding to a function, handing it back, and then all of that's happening under the just-in-time translation that Rosetta's doing. We can look into how the AOT file hash is calculated, so we can just like shove random gubbins in there. And we know that code is not signed, and we know that architecture preference is going to be kept because that's how like it works. So if we have a child process, it's also going to run under Rosetta. But having said that, we can also maybe like POSIX spawn like a native Apple Silicon application. We just have to do a bunch of syscalls. So this is like an example of how that hash gets calculated for a unspecified command that Rosetta uses. It's for when there are instructions in the just-in-time that are ready to be appended. So they've gone through that binary tree search and they're like, okay, this looks good, let's send it. It will essentially use this to then append those instructions to that AOT file. It's a whole bunch of stuff, but the long and short of it is like these hashes are like, I mean, SHA-256, I don't want to do that much math. But the math doesn't matter if it's like not that good, right? Like, it's just like stir len, offset. This stuff is pretty easy to defeat, and this essentially means like I can patch something, and as long as it's like an external library, the hash doesn't change. So whoops. So that's a bit annoying. This looks insane. I'm not reading all that. But like essentially I've patched it, and then I've looked for it, and it's the same hash. If it's not, someone can read it real quick. So, okay, we know all that. We know that Rosetta is built for like developer friendliness and to be quite fast. So one of them is child processes keeping that same architecture, well, the kernel's architecture preference for it, which is going to be that 86 running under Rosetta. There's a lot of other stuff that's pretty undocumented. So there is a function that Apple enable in one of their configuration registers. It's like the first bit where it enables total store ordering, which means every allocation you do, so like a sub stack pointer, it's going to do that at the time of it reading that command. There's a lot of stuff in ARM which is like weak store ordering, which will be like, look, babe, I'll do it. That's fine. So total store ordering kind of guarantees that it'll do that allocation at the time. So there's probably a bunch of other stuff that happens for like floating points and stuff, but I didn't look into it. There's really good documentation from Asahi Linux on the system registers that are undocumented from Apple. And also I found out just today that there is a Rosetta Linux. So essentially someone's using the M1 tool that Asahi Linux uses to kind of like put random crap in the bootloader. And then they force Rosetta Linux to run, and then they can do a bunch of debugging. So I'm sure there's a lot of stuff there in terms of looking at the characteristics of how the Apple Silicon chip itself is doing a lot of configuration stuff to kind of mimic as much as it can an Intel Mac. Oh, and obviously there's like a bunch of like registers for like pointer authentication and stuff, but pointer authentication is not something that's happening in Rosetta 2. That would be crazy. Right, so we can just like poison a dynamic library, right? So we could just like put system in there and then, I don't know, send it. Yeah, we could probably even like just patch a binary. So if there's a valid binary, we can just patch it instead of making our hello out with like an evil dynamic library. We would just need to figure that out. In fact, we could probably use a video game to do that. So yeah, we'll have a look at like Assault Cube, and this is like an example of how those stubs work. So the ahead of time translation has happened, and it said, look, I don't want to look at that. What I'm going to do is I'm just going to say, you're going to jump to SDL init, and you're going to figure that out. And that's just something that happens, and then the dynamic library will be pulled in, and it'll resolve the pointer to that specific function in that library. And like we've already talked about, DYLD will, well, DYLD and another kernel thing. It's got like a four-letter acronym. I don't know how to say it. We'll check like code signing, but we know that code signing is not important for Rosetta. So I'm sure there's a whole bunch of other avenues to look at how this could be leveraged. The fact that it doesn't check the code signature, but it will parse it. I'm sure there's a bunch of interesting things with that. But you could also squat an Apple developer account and then just like, I don't know, ship it and then just like get banned. So there's that too. This is not mine. This is David Dixon. Okay, so quick recap time, because I'm going a bit fast, so I totally get it. It's because I want to show it. But we know that these libraries resolve outside of the ahead of time process. That's cool. We know that the dynamic linker will grab this and resolve it, and then the JIT will get it and map it, and then we're all hunky-dory. We know that we can create child processes under Rosetta 2. We know that we could run some ARM64 if we know how to do it. And we can do simple IPC calls because we've looked at like how external cheats work, and that works just fine. So we're kind of good to go. Okay, well, let's make the game hack then. So we just need to find a function in a library. We've already looked at it, the SDL init, that we'll be looking at today. And then I'll be creating a malicious library that will install under that library. So many libraries on libraries. And then we patch it so that when Assault Cube runs, we just essentially get to run our malicious function and hand it over to the legitimate function. So I picked SDL2. That's like the graphics engine it uses. That seems like the most obvious thing. Game, graphics, start, things on my screen. We want to run that. So this is the lazy pointers section. So essentially this is just like going to be like zeros or garbage values or such. And this will get resolved by the dynamic linker when it starts running. So we know that it's there. And we can see that, oh gosh, this is tiny, sorry guys. We can see that the 12th thing that's gotten loaded when I pull image list, or 13th really, is the SDL2 framework. That's the shared library. And then it's just got the full directory for it. So it's versions A SDL2. That's what we're wanting to patch. And then we can see that it actually runs, right? Because I tried to do this with another function and I realized it didn't run. So you got to make sure it runs. So just make sure you see where it executes. This also would be like if you were designing like a malware, you'd want to look at where it executes anyway, because you might be wanting to get values that are currently in the register. But yeah, we know it works, and we can see the module file there as well, the architecture it's stating itself as, and the address. So that's awesome. So now we have to think about, okay, how do we get our malicious function to steal that legitimate function SDL init? There's a section in a dynamic library called data interpose, and essentially it allows you just to have a tuple of like 2 function pointers, and you can swap them around. I like to think the short way of saying it is like it's like DYLD insert libraries, but it's different technically. A thing here to consider is that, you know, if we had pointer authentication in this system, we would need to find a way to rebind it, and that's not implicit in using data interpose. So this is an example of it. So we're just defining it, we're chucking in the pointers, and then we're just swapping them around, and then we've just got our printf, and then we're saying, look, just chuck them over. And also, like, this is so, the use thing is so it doesn't like get stripped, because I used to compile a bunch of this getting ready for this talk, and I was like, it's not there. So yeah, use the attribute used. But yeah, that's how you can swap the function pointers. I love chess. All right, so let's do it for our one. So SDL init. The really crucial thing is that SDL init, when you hijack a function pointer, right, it still needs to do what the legitimate function is doing, because otherwise it would crash. So we just need to make sure we're preserving what it is taking as a function signature, and then we're implementing our interpose, and then we can essentially just run a code cave, which is all hunky-dory. There's some definitions of like the constructor and destructor as far as I can tell, this is just when dlopen is like opening up the dynamic library and saying like, hey, I want to like run this stuff, or I've mapped it, and it'll just run the constructor. So that's awesome. And you can see just there at the bottom, SDL init hijack. I've got the flag, so we're preserving it. And then I've just done like a really simple like fake bool that just looks over it. And then if we haven't hit it yet, we run our code. And if we've already hit it already, we'll just run the legitimate function. And yeah, so we've got that all good to go. So now we have to find a valid binary. Because we're pulling something from SDL2, we're going to use SDL2, but it's pretty much the same if you wanted to patch Salt Cube itself. We've got the swizzle to go, where we swap the functions. And yeah, damn, I don't know. Do we have to patch like a Salt Cube now? No, we don't. Like, it's in the header. Yeah, it's just all in the header, so you can just chuck it into the header. There's even definitions you can use for like a weak library. So if the library is not found, it'll still run. So that's brilliant. And we can do exactly that. So this is me just saying like, hey, I just want to make the evil dynamic library. Here's the framework for it. There's where I want to put it. And then I'm using lief. I know there's the install name tool command as well that you can use. But I use lief just to say, hey, go in SDL2. Chuck in this dilib command that it's a weak library. We can use the relative path of executable path, which is just a different way of defining relative paths relative to executable. And then we can remove the signature because we can use unsigned code. And this is essentially like how, hypothetically, I mean, I haven't looked at the pull rat malware specimen myself, but this is pretty much how it would work. And there's a video for it, but I want to show you guys essentially how it works. That's my giant Tim apple. All right. Damn, that is tiny. Let me see if I can make that a bit bigger. No, I'm making it smaller. All right. Cool. The reason I want to show it live is because there are a few flags that might be interesting to look through. Not clear. All right. All right. So that's it first. So I will quickly, hopefully not crash it immediately, but my code has both a ARM64 shellcode and an x86 64 shellcode. So the 86 shellcode is just, that's LLDB. And that's really tiny too. I can barely see that myself. All right, let's see what I can do. Clear. Temp. Yeah, so that's the AMD, the Intel shellcode. It's just printing something to temp. But the interesting one was that I could do a POSIX spawn shellcode to a native Apple Silicon processor calculator. So I will say the shellcode for native Apple Silicon, it's really not, because it's trying to like run under Rosetta, it's pretty unstable. So it was quite verbose and a lot of trial and error. But yeah, we can essentially run it, like just as long as we test it, which is great. And that's, I don't know, that's not good. I mean, it's good for a talk, but that's not good. So that's an example of like unsigned code in Rosetta, and then the fact that we can almost figure out the characteristics of Rosetta to then run almost whatever we want. There are a few things, like if we wanted to run something with like a native application, we would have to still consider code signing, but this could be an excellent primitive to look into, you know, using Rosetta for nasty and tricky things. So this is a really good, this was a really fun project, and I will get back to hopefully my I love like talking like that, and then I'm just like using the computer like I'm like 900 years old. That's so damn real. All right. Or not. Let me see. Sorry, 1 second. Okay, thank you. So that was just essentially the demo I wanted to show. There was some other stuff in there. If we do DYLD print interposing, underscores between it, we could also see that the swizzle was happening. So the dynamic linker will say, hey, I found this section of the dynamic linker, which is data interpose, and I'm just going to swap the function pointers. So that's pretty interesting. So, some really quick takeaways. I already went over a little bit, but essentially, Rosetta 2 has a bunch of characteristics that are really great in terms of like the intended, what was intended for, to be really friendly to developers moving to Apple Silicon. But there are like some considerations around running unsigned code, especially at this point. Game hacking is also just really fun. Like I wasn't looking too much into Rosetta until like stuff started crashing. So that was really fun to look into how that transpiler worked via making a game hack. I think this is like speculation, but Rosetta 2, it's going to live on in like the Linux virtual machines that they're offering. There's containerizing, the containers that they have now, and a bunch of like the game porting toolkit. I think game porting toolkit is going to be the most likely thing to inherit some of the stuff of how Rosetta 2 works. But who knows? And there's a lot of residual data for attribution, technically, but it's all hidden away. So you kind of have to like break a lot of defaults to even log this stuff, so that makes it annoying. But the most interesting thing, I think personally, is that Apple is not the only people that use this stuff to move their old binaries when they're making a huge business move to new architectures. We've got like, I think it was like recently, there was like yeah, like, I don't know if I trust this guy. The idea of RTX Spark is really impressive, really, really cool. I will just believe it when I see it in terms of like how this is all getting done. I don't know Windows as much, but essentially all of Windows on ARM is only JIT. And we've talked a lot about like how there are a lot of ways we can exploit the characteristics of having something stubbed and is like predictable because it's ahead of time translated. We can see it if we pull in a decompiler and we don't have to do any dynamic analysis. And then we can leverage the fact that it's going to call to something that is predictable, but in the just-in-time compiler, and it's just going to run with it. So I think this is going to be like a really interesting avenue for someone who is interested in the same idea. Just, look, I'm on the trendy machine, so you're going to have to find a less trendy machine. And that is me. I'll wrap it up there for like questions and answers. I'll put the code on Codeberg or when I get like, no, I think I'm unbanned on GitHub now. And I'll make a blog on my website, Kernel, to go over this, and I'll also put the slides up there as well. And if anyone wants to reach out to me afterwards, I'm on Mastodon, but you can also just pull me aside. We're here for 2 days, so I'll leave it there.
Did you report any of this stuff to Apple, and did they have a response?
So I no, but The thing is, it is difficult to describe this as a CVE because this is like the intended functionality of it. We're more so looking at like malware, so it's like intended use. Someone has already done the downloading of it, and now it's just all intentional running. So I could say like, oh, it's a security vulnerability, but it's already been reported on by Mandiant, and I'm essentially just going over that and how it would work with Swizzling. So I think it would be, I think it would be worth me reaching out to be like, hey, this is still a thing, but keeping in mind that it's now end of life, this major release, and that it is intentionally meant to be unsigned code, or it allows unsigned code, it makes a very difficult definition of like, is this a vulnerability or is this just like intended? So not intended malware, but it's like, this is like unsigned code being run. So, look, it's a good question. I wish there was like a more expansive view of like reporting a vulnerability. It's also not on their bug bounty page at all. Sorry, good question.
Thank you. Is this how you got your GitHub account banned? And if not, how?
So I haven't put this on GitHub. I put the first half on GitHub. I put assault cube offsets .txt, and that's what got it banned, like auto banned. So I think like maybe just be more obtuse with the name. No, less obtuse. Don't call it offsets.txt. That's dumb. They were actually really kind. They were like, oh no, we know that there's a bunch of educational repositories for Assault Cube at this point. So it was a pretty funny chat with the person who was on the support team at the time. Oh, sorry, thank you.
Hi, great talk. That was really great, a lot of information. That's great. So going back to kind of what you talked about, which is kind of silly to think about any attribute of a video game being a quote-unquote primitive, but that's really cool. So you mentioned health, is a good struct to look at when you want free memory. What about inventory? Because that inventory is something where there's, a lot of memory allocation and the deallocation that happens rapidly in like the vulnerability research community for video games. Do they kind of look into like use after frees with inventories, or are there any other kind of interesting free memory utilization that people look into?
Yeah, that's really good. I guess I'll restate it because I think I glossed over it a bit quick, but the reason why health is really interesting is because of the co-location of memory. So when we're allocating something, we're allocating not just like the integer size of memory, we're allocating like a bunch of stuff that is responsible for a player. There is another interesting part of it that is less useful when you're looking for like a health value, which would be something like an inventory, and that's because you want to know what types they're using. So they might be using like something that is just like 2 U sizes long, and you almost don't know what it is at all. But if you look at the inventory, I could think like, oh, they're just going to be like a bunch of enums or something like that, or like just a very short list of potential types. And that would make it really easy when you were designing a game cheat to understand how they're using and how they're defining types. For the use after free, I would say a way of looking at use after freeze and like kind of the order of memory allocation is especially important when you are making internal cheats. So for this, we're not considering anything because the anti-cheat doesn't exist when you're doing local play. But for example, really old Counter-Strike 1.6 cheats, you need to almost understand like the basic primitive of use after free, because you essentially need to like almost time the memory allocation of like whatever you're dereferencing and changing at the same time. So that would be a consideration, and that's really useful in terms of like general